thank you. It is a real pleasure to be here and to have a chance to talk to you about one of my favorite topics. What is the most important problem facing the world today? There's the answer. I think there is a problem with my slides. There we go. There is widespread agreement that we are facing a really important turning point in our history. The problem, of course, is the greenhouse gas emissions caused by the widespread combustion of fossil fuels. This generates carbon dioxide. It enters the atmosphere. Carbon dioxide enhances the natural greenhouse gas effect of the Earth's atmosphere and causes the temperature to rise. The effect on climate is perceptible already, and it's likely that it's going to get much worse. So what do we do about this? Already, many people are thinking about an energy transition. We need to think beyond fossil fuels about carbon-free energy. And of course, fossil fuels are widely used in transportation. We know how to deal with that, electrification. They're also used in buildings for things like heating and cooling and lighting, and again, electrification can potentially deal with that. But there's a third part of the problem, which fewer people are aware of. It's one that I'm very passionate about. I work in this area, and I want to tell you about it today and make you aware of it too, if you aren't already, get you thinking about what we can do about this area. All right. Apologies. We want to go forward. Here we go. So, the topic is the chemical industry and how it relates to this energy transition, which we are anticipating. And my perspective on this is as a chemist, as a chemical engineer. But obviously, I want to educate a lot more people about this part of the energy transition. So we'll start with a story. And it actually has nothing to do with the energy transition, but it has everything to do with how we perceive problems, okay? So a long time ago, the British Broadcasting Corporation broadcast a news segment on April 1st, April Fool's Day, describing a little town in southern Switzerland which was conducting its annual spaghetti harvest. Okay, and you can see the farmers here collecting the spaghetti from the trees, getting ready to make their dinner and also perhaps to sell their part of their crop to others who enjoy spaghetti. And this topic generated a lot of calls to the BBC by concerned people who wanted to know how they could get a spaghetti tree for their own use in their garden, and how to ensure that the spaghetti strands that grew on the tree grew to exactly the same length. How do you do that? How do you get them all the same length when they grow on the trees? And of course, at this time, this is 1957, there really were not a lot of people who had a great familiarity in the UK at the time with spaghetti. It was a bit of an exotic food, not the ubiquitous favorite food that we know today. People didn't actually know where it came from, and that's why the hoax worked. So where does our stuff come from? And I want to think much more broadly about stuff now, although spaghetti I could include in this list as well. Where do our shoes come from and our clothes? Where do our soaps and our detergents come from? How about our fertilizers and pesticides? What about paints, adhesives, all this stuff? Well, I know what I do. I go to the store, or maybe I go online, I look for a vendor that sells this stuff. And so this stuff comes from manufacturers that we know. And you recognize some of the brand names. Of course, there are many, many more. These are companies that manufacture stuff that people want to buy, that we find useful. But let's go further back in the supply chain. Where did these companies get their stuff to make these materials? So they get it from the chemical industry. And the names of the chemical industry companies, these are the major companies, probably less familiar to the general public. You don't see these in the supermarket or on Amazon. You see the names in the middle of the slide. But these companies make the stuff that goes into making our stuff. And so we can go further back still. Where do the chemical companies get their stuff from? And what is this stuff anyway? All right, so the answer right now is that most of this stuff comes from oil. And we convert oil into a group of materials called petrochemicals. And you can understand why. They're chemicals and they come from petroleum, okay? So what's in this barrel of oil? The barrel, by the way, is 42 gallons. It's larger than a barrel of beer, which is only 31 gallons, and I have no explanation for that. The petrochemicals in a barrel of oil are actually a tiny fraction of the total. So you see here in yellow, most of a barrel of oil is used to make transportation fuels, about 70%. There's another quarter which goes to make gases and solids, things like asphalt. And the tiny red sliver is the petrochemicals, about 3.5%. Okay, so a tiny part of a barrel of oil. And yet, the amount of energy that goes into making those petrochemicals is enormous. It's an enormous fraction of the US economy, the US energy use, and the value of the petrochemicals is enormous as well. Okay, so the numbers on the slide show the value of that big fraction, the 70% in yellow of the transportation fuel, compared to the value of that tiny red sliver of petrochemicals. They're almost identical. Okay, so enormous value and enormous energy, both embedded energy in the hydrocarbons, which are in this barrel of oil, and in the processes which generate the petrochemicals from the barrel of oil. All right, if we look at this globally and put this in the context of all the energy that we use, it's interesting to see where our energy comes from. And I think you can see now that energy and petrochemicals are twins. They're linked together, inseparable. All right, so this is a chart of energy use as it stands today on the far right-hand side, and you can see the fossil fuels there, coal, oil, gas. They constitute about 80% of the world's energy consumption, hence the problems with climate change due to their greenhouse gas emissions, okay? And on the top, there's a little sliver which represents the renewables, about 15% today, biofuels, solar, wind, hydro, those kinds of things, and a little bit of nuclear. Okay, now I've been directing your attention to the far right-hand side of the graph. Let's look at the axis label on the left. These are in hundreds of thousands of terawatt hours. So what is a terawatt hour? Well, tera is a prefix which indicates that we have basically a billion watts, okay? So a terawatt is a billion watts. So the total global energy consumption is about 170,000 billion watts, hours. And that's a lot, okay? Another way to think about it is it's 170 with 12 zeros after it. And where else do you find numbers with that many zeros after them? Anybody taken an astronomy class? These are astronomically large numbers. It's hard to get your head around. And so what we're going to do, instead of talking about these immense numbers, is convert them to a more useful sort of range of numbers to think about. These are quads, okay? So a quad is a quadrillion. And unfortunately, we change units from terawatt hours to British thermal units, BTUs, which are also used in the energy industry. Engineers love to change units around. But a quadrillion BTU is one quad. And so the world's energy consumption right now is 600 quads, okay? The US alone uses about 100 quads a year, okay? We're a major user. And the chemical industry, or industry as a whole, is about a third of that, and the chemical industry is the largest industrial user of energy. So it's a very significant fraction of the world's energy use, the chemical industry. And the petrochemicals, you see them you see the origins of them here. Now, another interesting thing about this particular graphic is that you can see about 150 years ago, another energy transition, which we might be able to learn something from, right? Because 150 years ago, the world essentially ran on biomass, not fossil fuels. And so we've gone through this transition one time already. It has completely changed the way people live. And we are expecting that the next transition will change the way we live as well. The way it changes the chemical industry will change the way that you and I and our children live. And so that's why it's really important to think about this now. All right, so when the world lived on biomass energy, the carbon cycle was balanced. Every element has a geochemical carbon cycle, a geochemical cycle. This is the one for carbon, and it shows carbon dioxide from the atmosphere being fixed by photosynthesis, becoming plant matter that may decay and go back into the atmosphere as CO2, or it may get buried and eventually become part of the sediments or part of the rocks. And you know, the sources that are putting carbon dioxide into the atmosphere, the sources that are pulling the sinks that pull carbon dioxide out of the atmosphere, essentially balanced. So what changed with this energy transition 150 years ago was the sudden and rapidly accelerating addition of fossil carbon to the atmosphere. Carbon that had been buried for millennia, came from dinosaurs originally, very, very old organic matter that had been buried for a long time, which is now being emitted to the atmosphere. And it will eventually suffer the same fate as all carbon dioxide in the atmosphere. It will go into plants, it will go into the oceans, it will become part of the sediments. But that sink will take about 2,000 years to re-equilibrate the carbon dioxide in the atmosphere. And I don't think we have that long to wait. All right, thinking now about this original energy transition, what drove it, and how we think about the next one. It's kind of interesting to realize that at the time when coal was first used and then oil was discovered, it was considered to have tremendous environmental benefits. People were really happy about the discovery of oil. One thing that it did was it absolutely annihilated the whaling industry. Okay, we used to slaughter thousands of whales every year to extract the oil to light our homes in these whale oil lamps. And that completely disappeared once we had cheap, reliable, clean kerosene lamps. That's on the energy side. It changed chemistry as well, and the chemical industry as well. Here's an example showing, this is a hawksbill sea turtle with a beautiful shell. And it was hunted nearly to extinction for that shell to make exotic, very beautiful jewelry, including combs. And once we had oil to work with, we could make materials which looked quite similar for a tiny fraction of the price without killing any sea turtles. That was considered to be a very good thing. And there are many stories like this. Ivory from African elephants. Elephants were killed for their tusks to make things like billiard balls and other things that you can make out of ivory. We don't do that anymore, and there's no need because we can make these things very readily from petrochemicals. All right, looking now towards the next energy transition, towards the future, and starting with where we are today. So this is our energy mix. Remember, it's about 80% fossil fuels at the moment, and about 15% renewable, and about 600 quads total around the world. Okay, so where are we going to be in 2050? This is a crucial period of time when we need to achieve this energy transition. And here is the best prediction from the US Energy Information Administration. And they predict that in 2050, the renewables will constitute about 28% of the energy mix. So they're growing rapidly, but still only 28%. Fossil fuels will decline to about 70% from 80 today. This doesn't sound very encouraging, right? And one of the reasons is not only that these technologies are difficult to implement on a large scale, but notice that the amount of energy is going to increase, the energy demand is going to increase by 50% as well. So why is it increasing so much? World energy consumption is predicted to rise because the demand, principally from these countries called non-OECD countries, is going to rise dramatically. So the US is an OECD country, the Organization for Economic Cooperation and Development. And it's a group of about 38 industrialized countries, wealthy countries, that have, at this point, fairly stable energy needs. But the rest of the world has very long way to go before they consume energy at the rate that we do, and their energy demands are rising, in part because their population is rising. And population of OECD countries is pretty flat. That's not true in the non-OECD countries. Also because the wealth of those countries is increasing, and it's increasing at a much faster rate than the wealth in the OECD countries. Okay, and so why is this linked to energy? I mean, of course, it's you want people to be wealthier, to have a better standard of living, but why is it linked to energy? And the reason is that there's a very tight correlation between energy consumption and GDP, which is the wealth of the country. Okay, so we have this nice linear correlation here. You see the United States, top right-hand corner, we have a very high standard of living and a very high energy use corresponding to it. And the rest of the OECD countries are all in that top right-hand corner. But the countries that are in the middle and the ones that are in the bottom left-hand corner are moving along this trajectory. So they're using more energy and improving their standard of living. It even comes down, actually, to the food that we eat. And the consumption of food calories is far higher in OECD countries. It's about a third higher in OECD countries than in non-OECD countries. You can see where the wealthy people live. Okay, you can see their consumption of energy. This is a NASA satellite image which shows you where energy is being consumed very, very clearly. So I mentioned food. Food is very important to all of us, and we need to grow food and supply it to more places. How hard can this be? What do you need to grow food? Well, obviously, you need sunlight, and sunlight is free. That's great. But you also need fertilizer. And fertilizer, in terms of energy content, is not free. This is a very high energy material that the chemical industry makes a lot of. Okay? You need machines to plant and to irrigate and to harvest. And you not only have to build those machines, but you have to fuel them as well. You need trucks or trains to take the food to market. And in the supermarket, you need packaging to keep the food fresh. And so the energy in our food system alone is very significant. About 15 to 20% of global energy just goes into the food system. This is a place where it's very difficult to decarbonize. So of course, we should do as much decarbonization as we can. People are looking more seriously now at electric cars, at wind power, at solar power, et cetera. But let's think about this another way. It's great to have an electric car, but you still have to have the stuff to build the car. You need metals. You need the battery, the stuff that goes into the battery. You need plastics, fibers for the interior. You need stuff to build windmills. You need stuff to build solar panels. So you can't think about the energy transition without thinking about the stuff. It's not just about the electrons. All right, so if we're going to electrify things as much as possible and still think about the intermittency of renewables, we have to think about energy storage as well. This is another part of the puzzle. And this is a graph which shows the volumetric energy density, how much energy you can pack into a liter of material as a function of the gravimetric energy density, how much energy is in a kilogram of the material. And the desirable energy storage material will have a high volumetric density and a high gravimetric density. So on this graph, things are all over the map, but where are the desirable materials? They're the ones that are closest to the top right-hand corner, and you know what? They're all hydrocarbons. Why hydrocarbons? It's because the energy in carbon-carbon and carbon-hydrogen bonds is very high, and it's very compactly stored. These are lightweight materials with very high energy density. In fact, it's higher than some of the molecules that nature uses, like fats and sugars. It's much higher in terms of volumetric energy density than hydrogen. And look at where batteries sit. The batteries are in the bottom left-hand corner. Batteries are terrible at energy storage. So if we want to store energy on a global scale, hydrocarbons are a very interesting contender, and we know how to use them because we have 150 years worth of experience with this. So the petrochemical industry is an industry that focuses on transforming hydrocarbons for the most part. It takes those fossil hydrocarbons, natural gas, oil, and sometimes coal, and turns it into things like fertilizer, plastics, other kinds of materials. And if we want to transition the chemical industry away from these fossil feedstocks, as we call them, we have to think about how to do that, because we're not going to get rid of the stuff and the need for the stuff. We have to just think about how to make it differently. The largest energy users in the chemical industry are truly enormous. These are individual processes that by themselves use a significant fraction, like a few percent of the world's energy. Steam crackers, okay, which take saturated hydrocarbons like ethane and turn them into olefins like ethylene. And these facilities are enormous, cost $1 billion to build one of these. The ethylene is turned into plastic, polyethylene, in similarly very large facilities that use an enormous amount of energy as well. And the bottom right, you can see a Haber-Bosch plant. This plant is turning nitrogen into ammonia, which is used to make fertilizer. This single process uses about 3 or 4% of the world's energy, okay, and feeds a lot of the world's population. So in the future, how are we going to do this? We have to transition from these billion-dollar chemical plants that use fossil carbon feedstocks, convert it into petrochemicals, and then we use them and discard them in this sort of linear carbon life cycle. We need to reimagine this, perhaps as a biorefinery, perhaps as a smaller scale chemical plant that takes other forms of carbon, turns them into the stuff we need, gives them to us to use, or gives them to the people who will turn it into stuff that we want to use, and then takes it back again and turns it into new chemical materials. And perhaps the feedstocks that go into these new chemical plants will come from the fields around the chemical plant. It's possible. All right, so where's this renewable carbon going to come from? I mentioned the biomass already, and crops like switchgrass, fast-growing grasses are a possibility. Agricultural residues contain a lot of useful fixed carbon. We could perhaps pull CO2 right out of the air. Costs more energy then to reduce it because the sunlight has not yet done that for us in the plant, but that's a possibility as well. And then there's our waste, our food waste, our plastic waste, all kinds of waste that contains carbon in a high energy form that we can potentially extract. All right, so how would we actually do this? It sounds nice in principle. The chemistry is actually to be discovered for the most part. People have been thinking about this for a while, me included, and here's one example of taking vegetable oil with a catalyst. A catalyst is a material that allows you to rearrange the bonds, and this molecule, methyl oleate, comes from vegetable oil. Every line represents a carbon-carbon bond in this molecule, and methyl oleate is biodiesel. Right? So you can very easily make biodiesel, make a fuel out of vegetable oil. But you can do other things too. You can cut this molecule in half. You need a different catalyst to do that. When you cut it in half, you make two fragments. The fragment that is just carbon, all you see are the lines, so there's only just carbon bonds here, can be used to make lubricants and oils. The fragment that has the oxygen, that fragment with all carbons can be further modified to make surfactants. You can make shampoo out of this very easily. And the fragment that has the oxygens can be used to make plastics, okay? All from vegetable oil. Sounds really nice. There's a problem though. This is food, right? We're diverting food to make chemicals, and we don't want to do that. So the next transition The harder one, actually, is to take the non-edible part of the biomass, which is called the lignocellulose, and turn that into chemicals. It's a much harder problem because the lignocellulose is not a nice pourable liquid with molecules that react very, very readily. Lignocellulose is the stuff that makes trees stand up. It's the plant cell wall. It has three components: cellulose, hemicellulose, and lignin. They're all polymeric, so very large molecules, very insoluble, and we need to get them out of the plant in order to be able to get the carbon out in a usable form. So it can be done. Again, the key is this technology called catalysis. And so you can literally take raw biomass, sawdust if you like, over the right kind of catalyst and turn it into liquid fuels. But we can be even smarter about this. We don't only want to make fuels, we want to make chemicals this way. And if we want to do selective chemical transformations on these molecules, we need carefully designed catalysts that have special architectures. So here's one of my catalysts. It's a mesoporous material. You can see a cartoon on the left and a micrograph on the right that shows these pores inside going into the catalyst. And inside those pores, we implant active sites that cause these chemical transformations to occur. So biomass molecules go in, they come out the other side being transformed when you design them correctly. This is the latest thing that we're working on. It's really exciting to be doing this, and we got a lot of good press about this lately. Taking waste plastics, post-consumer plastics, and specifically polyethylene, which is a plastic which is hardly recycled today, and turning it into small molecules that become part of the petrochemical value chain, or replacement for petrochemicals in the value chain. So you see a large polyethylene molecule going into the reactor, which contains a catalyst. What comes out of the reactor, two kinds of molecules. The top one, which is just these carbon-carbon bonds, nothing special about that, that's your motor oil. The bottom one is really exciting because that one has this six-membered ring colored in orange. That's an aromatic ring. And this molecule is a very good precursor to anionic surfactants. So you can make surfactants, make soaps and detergents out of these molecules. So we can do this without using any new petrochemicals. It's actually using the waste that comes from our society at the moment. So I'll end here by saying that Santa Barbara is a place where scientists and engineers care about the environment, care about social responsibility, care about making a difference. And if you think that putting all of those things together is hard, you're right. If you think it's exciting, then you're in exactly the right place. Thank you.